talk about parametric functions today. And this is really what the rest of the unit is about. Basically, parametric functions are an alternative way of describing graphs. It's a very powerful and flexible set of tools that allow you to do things that ordinary functions would not allow you to do. So let's start off by defining them. A parametric function is a pair of functions. One of them we'll call x of t, and the other one we'll call y of t. So a parametric function is really a pair of functions, x of t and y of t, which both depend upon a single variable t. And that's kind of it. It's a pair of functions, all right? One of them is called x of t, one of them is called y of t, and both of these functions are functions of the same variable t. Now, I said that parametric functions are a new way of describing graphs. So I want to talk about how do you graph a parametric function. So given a parametric function, sometimes, by the way, people put the x of t and the y of t in parentheses, like this. How do you graph it? So how do you graph a parametric function? Well, this is kind of the question that we'll spend a lot of the unit answering. So it's a question with many different answers, and how you do it depends upon the situation. But the most basic elementary way of graphing a parametric function is point plotting. Point plotting. You plug in values and then you plot points. So here's what you do. Pick a value for t, plug it in to your two functions, x of t and y of t, and then you plot the resulting point in the plane. And then you just repeat that again and again until you have a graph. That's what the parametric graph is, okay? So, for example, consider the parametric function given by, let's say, 3 cosine t, comma 3 sine t. Okay, what does the graph of this thing look like? Well, to have a little bit of a sense, what you could do is start plugging in values for t. So maybe I'll start with t equals 0. If I plug in t equals 0, that's going to give me 3 cosine 0, comma 3 sine 0, which is 3 comma 0. So the point 3 comma 0 is on the graph. Okay. Then plug in t equals, well, because the functions here are trig functions, I should probably pick like nice angles so I can actually evaluate them. So maybe like, I don't know, pi over 4. If you plug that in, you're going to get 3 cosine pi over 4, which is like 3 root 2 over 2. 3 sine pi over 4, that's also 3 square root 2 over 2, which is about, let's see, what is that? 3 times square root 2 over 2? That's like 2.12, comma 2.12. And so you would plot that point on the graph. And you just keep doing this, okay? You just keep doing this until a nice picture emerges. If you plug in t equals pi over 2, then you're going to get 0, comma 3, right? And if you do this, then you'll eventually get a bunch of points. You connect the points with a smooth curve, and that's the graph. If you're curious, this parametric function right here actually happens to represent a circle of radius 3 centered at the origin. There's a couple of ways that you can test that using technology. If you've got Desmos in front of you, Desmos does understand parametric functions. You've got to enclose them in parentheses, and you've got to use the variable t. So if I type 3 cosine t, comma 3 sine t, it understands what I'm talking about. Oh, you'll notice it only traced out a little bit of a curve. I claimed that this was a circle. The reason why is that right now it's only plotting points on this curve, as you can see here, for t values between 0 and 1. But I think that to see this entire curve, I would probably need to go from 0 to 2 pi. And there's the full circle. Okay. Oh, by the way, the variable t is sometimes called the parameter. So let me just add that to the notes. T is often called the parameter. Okay. You can think of it as like time. You can kind of think of the curve as being swept out as time passes. Let me show you what I mean. So on Desmos, I'm going to change the maximum t value to a letter, A, and then it lets you add a slider. Okay? So because A is set equal to 1, right now the graph is being displayed for t values between 0 and 1. If I change the value of A, it's changing the range of t values that it's plotting. So as t increases, you can see that more and more of the curve is being swept out. So you can kind of think of t as like representing time and the parametric curve being swept out over time. And that's kind of interesting because that means that like parametric graphs actually have an orientation to them. Like they kind of have a direction, you know what I mean? The graph of this thing, yeah, it's a circle, but it's oriented. It's got a direction that points in this way, in the counterclockwise direction, because as t goes on, that's the direction in which the curve is being traced out. So I don't think we're doing much parametric graphing today, but in the future, when you do graph parametric functions, we'll ask you to sort of draw a little arrow on the graph to indicate the direction in which the function's being traced out. So, yeah, so, you know, one of the advantages that you might notice right away of parametric functions, if you're trying to graph a circle in Cartesian coordinates, you need, I mean, you know, you sort of need two functions, right? You need like positive square root and negative square root. Parametric curves let you do all kinds of crazy things. Like parametric curves can be very, very crazy. Like if I just start throwing in some t's and stuff like that, you know, I can get spirals. I can get, you know, I can get like, if I do something like this, I mean, you know, you can get some really wacky stuff with using parametric graphs. So basically, parametric functions allow you to get graphs that you just like never could get just by using Cartesian. Yeah, so they're very, very cool. I'm just looking at my notes here to make sure I don't forget anything. There's a lot to say. Oh, before I move on. So that's parametric functions on Desmos. Pretty cool. How do you do it on the graphing calculator? So here I've got an emulated graphing calculator from TestNav. And if you remember, when we did polar graphs, you would have to hit mode and then go down here and switch the function from function to polar over here. But you can see this option right between those is parametric. So that's what you want. So if you want to do parametric graphs, first step, you've got to change it to parametric. Press enter. Okay, so now I'm in parametric mode. Now, if I press y equals to enter a function, you can see that each graph has two functions. I've got one line for x of t, and then the second line is for y of t. So if I wanted to do the graph that we were looking at a second ago, I'd be 3 cosine. And again, for the variable, it's the same button as always. It's just this button right here, but now it's a t. So 3 cosine t, 3 sine t, and now if I hit graph, there it is. Of course, you know, the aspect ratio of the window is kind of stretched. You can fix that if you go to zoom and then choose z square. That will adjust the aspect ratio so that it's actually, you know, like looks right. You might also have to mess with the settings on T. Like on Desmos, I had to adjust the maximum T value that it would draw. That's all changed in the window button here. You can see T min, T max, T step. These default settings look pretty good. If your T step is too big, then like your graph will look kind of stupid and blocky. Like if I just type in 1, you can see it looks like a hexagon or something. And what it's doing is it's just plugging in certain values of T and then connecting them with straight lines. If you're not plugging in enough values of T, then it's going to look jagged, not like a smooth curve. T step is controlling like the increment, how much T is going up by each time. So it should be a pretty small value, and that'll give you a smooth curve. If you make it too small, though, it'll wind up plotting 1,000,000 points, and it will take a long time, so you've got to find sort of a happy medium. Yeah, so if you're... Yeah. Okay. One important point that I've got here on my notes here, parametrizations are not unique. Okay? Like, in other words, you can have multiple different parametric functions describing the same graph. All right? Like a second ago, we were looking at, let me just restore this back to what it was. We were looking at 3 cosine t, comma 3 sine t. And we found that that was a circle. Cool. But if I make this 2t, it's also a circle. You might wonder, what's the difference? The difference is actually just... I mean, there's no difference in the graph. However, what you might notice is that the curve gets traced out faster. It gets traced out more quickly. Okay? Like, in fact, the curve is complete when t is only 3.1, when t is only 1 pi, right? You only have to go up to t equals 1 pi to complete the circle. So it's going twice as fast, right? And if I did like a 1/4 or something, then it would be traced out more slowly, right? You can see I'm cranking up the t value and it's like barely moving. So the same graph can have many different parametric descriptions, is what I'm talking about. You can also change the direction in which it's traced out by like putting negative signs on every instance of the t. Now this guy is going to be traced out in the opposite direction. It's still the same graph. It's still just a circle of radius 3, but it's being traced out differently. Okay? So that's one thing. Now, one example I want to talk about is parametrizing an ellipse. Okay, so if we consider the parameterization 4 cosine t, comma 8 sine t, that is going to be an ellipse. There it is. Now, why is this an ellipse? Well, with experience, you'll sort of just know by looking at this kind of thing that it represents an ellipse. How exactly do you know for sure that this represents an ellipse? One way to do it is, just like we could convert between polar and rectangular equations, it is possible to convert between parametric equations and Cartesian equations. All right? So I'm going to take this guy and I'm going to convert it into x's and y's, and we'll see that what we get is the equation of an ellipse which is centered at 0 and which has a major axis of blah, 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 blah. Okay, so let's see how that goes. So, example, convert the parametric equations. What was it? 4 cosine, 8 sine? Yeah, 4 cosine t, comma 8 sine t to Cartesian. All right, well, how do you do that? Well, here's the big idea. Cartesian equations involve x and y, but not t. Okay? Right now, we have that the x-coordinates of points on the graph are equal to 4 cosine t. So I can write x equals 4 cosine t. And the y-coordinates of points on the graph are equal to 8 sine t. What I need to do is take these two equations, and I need to do a bunch of algebra and somehow eliminate t from the equations. This is actually pretty hard to do in this example. Other examples it's easier to do. Maybe I'll do an easier example after this just to show you that it's not always so hard. So how can you eliminate t? I mean, you might think, oh, I should like solve for t in this equation and then substitute into the other equation. Theoretically, that could work, but that like, can you really solve for t in this equation? I mean, you'd have to like take the inverse cosine or something and then plug that into here. You'd get like a composition of regular and inverse trig functions. That gets pretty nasty. There's a better way of doing it. Here's what you should do. Square both equations. Like square both sides of both equations. The first equation gives you x squared equals 16 cosine squared t. And the second equation, if you square both sides, gives you y squared equals 64 sine squared t. And now what you do is just add both equations together. The left sides, when we add them together, we get x squared plus y squared. And the right-hand side gives us something not very good. Oh, I'm making a mistake. Sorry. It's been like a long time since I've done one of these. Oh, a year anyway. Before you square both sides, you need to isolate the trig functions. Sorry about that. Yeah, that's the trick. You got to isolate the trig functions, then you square both sides, then you add them together. That's the trick. So isolate the trig function. So get the cosine by itself, get the sine by itself. So the first equation becomes x over 4 equals cosine t. Second equation becomes y over 8 equals sine t. Then we square both sides. First equation becomes x squared over 16 equals cosine squared t. Second equation becomes y squared over 64 equals sine squared t. Then we add the equations together, and we get x squared over 16 plus y squared over 64 equals cosine squared t plus sine squared t. And this is where the t will disappear. Remember, the objective is to eliminate the parameter t. A Cartesian equation should only involve x and y, not t. And hey, look at that. That's just 1, right? That's just 1. So you get x squared over 16 plus y squared over 64 equals 1. Sure enough, that's the equation of an ellipse. So that's kind of a proof that this thing represents an ellipse. Another idea that might suggest to you that this is some kind of an ellipse, one thing you might notice, and this idea is going to become really important, not so much today, but in the coming days. The thing is, this guy right here is a formula for the x-coordinates of the points on the graph. But this function, 4 cosine t, it has a very restricted range. The function 4 cosine t can only take on values between -4 and +4. That means that the x-coordinates of the points on the graph must all sit between -4 and +4. And hey, look, that's true for the ellipse. Same thing is true for this guy right here. This guy right here is a formula for the y-coordinates of the points on the graph. But look, the range of this function is quite restricted, right? 8 sine t can only take on certain values. It can only take on values between -8 and +8, which means the y-coordinates of the points in this graph must all be between -8 and +8, and that's true here. And that's true. So that's a little bit of a clue. Hey, I'm looking at a graph such that the x-coordinates go between positive and -4, and the y-coordinates go between positive and -8. This ellipse is not the only graph having that property, but it's not super surprising, right? I think when you think about it that way, that the graph looks like this. Anyway, what else do I want to say? One nice thing about parametrics is that it's very easy to translate them. Okay, it's very easy to translate them. So if we wanted to take the ellipse that we've been working with, this guy right here, and I wanted to translate it. Translate 4 cosine t, comma 8 sine t. Let's say 3 units left and 2 units up. It's very easy to do that. You literally just subtract 3 from the x and then add 2 to the y. That's it. That's all you do. Why does that work? Well, basically, remember, this first function here is a formula for the x-coordinates of the points on the graph. Well, if you subtract 3 from that formula, what you're doing is you're subtracting 3 from the x-coordinates of all the points on the graph. In other words, you're moving them all 3 units left. Likewise, this guy here, that's a formula for all the y-coordinates of the points on the graph. If you add 2 to that formula, you're adding 2 to the y-coordinates of the points on the graph. In other words, you're moving it up by 2. So translation is very, very easy, okay, in parametrics. That's definitely one of their advantages. In the packet, there are some problems that I want to discuss. We ask you to try to draw this shape or something similar to it using your calculator. Right now, don't worry about the vertical lines. You might think that horizontal and vertical line segments would be easy in parametrics, but they're actually rather tricky. So right now, I wouldn't worry about these vertical lines, but try to get these 2 ellipses, okay? How do you know, now, like, how do you know the formula? Well, basically, what you need to do is you need to look at the ellipses and say, okay, I notice in this first ellipse that the x coordinates of the points in this ellipse, they all go between 2 and 8. That means that for this ellipse right here, my formula for the x coordinates must be a function whose outputs go between 2 and 8. Okay? Between 2 and 8. Well, I think that you can make that happen with some kind of a cosine function, right? Like, I think if you do I think 3 cosine t plus 5, I think that function will range between 2 and 8, right? It's like 5 minus 3, 5 plus 3. And then for the y-coordinates, well, it looks to me like the y-coordinates are all going between 9 and 11. So you need to write down some function whose outputs go between 9 and 11. Do that with some kind of a sine function. You might wonder what happens if you choose like cosine for both instead of cosine and sine. Interesting question. You won't get an ellipse. You'll get something else. If you're curious, take a look. Use Desmos or use your calculator to figure it out. So that's introduction to parametric equations, parametric functions, parametric graphs. Incredibly useful stuff, really cool stuff. There's one more thing I want to mention on the classwork and homework. So you're working on day 4. which looks like this. And this first page asks you to consider this sort of real world example. It's showing you the rabbit population over time, and it's showing you the fox population over time. And you'll fill in a table and you'll plot some points. The idea is this can be understood as a parametric graph because the rabbit population is a function of time, t, and the fox population is a function of time, t. And what you can do is you can get the graph by eliminating the parameter t. That's essentially what you're doing here. Okay, you're going to plot some points. You're going to get some weird ellipse of some kind. In the homework, they ask these questions. They give you this fox and rabbit population problem, and it's a little weird. There's some language in here that's kind of strange. What I want you to know is that essentially, depending upon the overall population of the rabbit and the foxes, you'll get different kinds of behavior. Like if, for example, the rabbit population is 10,000 and the fox population is 1,000, then you're looking at this dot right here, approximately, okay? And what's going to happen is, if that's the current population of the rabbits and the foxes, then over time, the population of the rabbit and the foxes will sort of go through this cycle right here. Both the rabbit and the fox population are changing over time. It's like a predator and prey thing, right? Foxes hunt the rabbits. So as the fox population increases, the rabbit population goes down, but then there's not enough food. So the fox population comes down and the rabbit population goes back up, and you get this cyclical periodic behavior here. But there's different kinds of cycles. This is a cycle where the population is changing a lot. Both populations are changing a lot in each cycle. But in a smaller ring, the populations are not changing so much, right? Like here, this ring is quite small. The rabbit population and fox population just isn't changing that much. And there's this point right here in the middle where everything is like in perfect harmony and the population like doesn't change at all. The questions they ask you questions about like, oh, what happens if you add more rabbits? What happens if you add more foxes? Does the wildlife biologist need to like take action to maintain the population balance? I think what they're talking about there, and I wouldn't worry too much about it, is just like, if you go in this direction, the populations are less balanced, right? Like if you go further away from the center, then you're looking at a larger ring, larger fluctuations in the population. That's less balanced. So I think the question is based when they're asking about balance, I think they're just sort of asking like, the change that the scientist makes, is it moving you to a larger ring or is it moving you to a smaller ring, right? More balanced or less balanced. That's all that's getting at. But don't worry too much about the language. So yeah, and then there are these problems here. Try to get, parametric descriptions of all these ellipses. I think you can do this guy as well. That's like a semicircle. But as far as the lines, don't worry about the lines, guys. Like it's kind of annoying. So anyway, that is it. Hope it was interesting. Have this stuff done, classwork and homework for tomorrow. I will see you all tomorrow. Also, don't forget to work a little bit each night on the review of the graphs that I talked about. Right, that worksheet with like the 40-something different graphs. Make sure you're doing a little bit of that each night. I want you to have it all done basically by this week. Okay, so like Monday of next week, it should all be done. We won't need all of it right away, but we will need all of it eventually. Okay, see you guys all soon.